Hi, welcome to this lecture on analysis of algorithms. So here we're going to talk about complexity of algorithms, which involves two parts. One is time complexity and the other is space complexity. Now, when you write programs that process large amounts of data, there are two questions that you ask yourself. The first one is, how long does your program take? Meaning, what's the time complexity of the program? And the other question is, how much memory does your program need? And that's the issue of space complexity. Let's first start with time complexity and see how you figure out the time complexity of an algorithm. For this, we're going to use a problem called the Threesome Problem as a running example. Right? So here's the Threesome Problem. You are given n integers, a collection of n integers, and you're asked to find out the number of triples a, b, and c, where the order is irrelevant, such that a plus b plus c equals 0. All right? So you're given a collection of n integers and you're supposed to find triples a, b, c, where the order is irrelevant, such that a plus b plus c equals 0. So that's the Threesome Problem. And the Java code that you see here solves this problem. All right? So the program is called Threesome and it is implemented in two methods. The first method is called count and the other method is called main. So let's start with the main. So the main method receives a command line argument, which is the name of a file that contains the n input integers. All right? So we read that file using the in data type. So we first create an object of type n, giving the constructor an argument, which is the name of the file that contains our input. And then using the single method read all ints from the in data type, we read the entire file as an array of integers that we call a. Okay? And then what we do is we create an object of type Stopwatch, which we will discuss soon. This object is called timer. It's an object of type Stopwatch. And then we simply make a call to this count method, giving it the array a as input. And what is count going to do? Well, it's going to return the number of triples that sum to 0. Okay, so it's basically solving the Threesome Problem. And that value is assigned to this variable, which we later print. Right? We not only print the count, but we also print the time that it took for this method to solve the problem. And how do we get that time? Well, we make a call to the elapsed time method from the Stopwatch data type. Right? And since we are asking for the elapsed time here, and since that is right after the call to count, and since count is the only thing that sits between the creation of the stopwatch and the point where we ask for the elapsed time, this time that we get back from the stopwatch is basically a very good estimate of how long count took to solve the Threesome Problem. Okay, so what are we printing for output? We are basically printing the time that it takes to solve the Threesome Problem of size n, right? And we also print the count itself, meaning the number of triples that sum up to 0. Okay, so now let's look at the count method. So the count method receives the array a containing n integers. So we first get n as simply the length of the array, so that's the input size, and then we initialize a variable called count, which to the value 0, and this variable is going to store the number of triples that sum to 0. All right, and that value is finally returned here. So how do we figure out the number of triples that sum up to 0? Well, we do that using 3 nested for loops. All right, and pay attention to the loop variables. So I starts at 0, goes all the way up to n in increments of 1. Now j doesn't start at 0, but it starts at I plus 1. And then it goes all the way up to n and in increments of 1. And then k, again, doesn't start at 0, but it starts at j plus 1 and goes all the way up to n in increments of 1. So when you set up these loops in this manner, you guarantee that you enumerate the triples of A exactly once. So each triple is exactly is enumerated exactly once, right? So you disregard the orderings. So for example, A, B, C is looked at exactly once, all right? And that's what we want here. Okay, and then inside of the innermost loop, what we do is we check if the elements in A at I, J, and K sum up to 0 or not. If they do, then we increment the count variable by 1 because we have just identified a triple that sums to 0. Okay, so we increment count by 1. And we keep going. And once the outermost loop is done, we simply return the value of count, and that is the number of triples A, B, C such that A plus B plus C equals 0. Okay, so the count method does solve the threesome problem of size capital N. Let's look at some input and output. In the first instance, we run threesome with the input which is a file called 1k_int_text. So this file simply stores 1,000 integers. So that is given as input to this program, and the program comes back with two things: the time that it takes to solve the threesome problem of size 1,000, so this number is in seconds, and then it also comes back with the count, which says there were 70 triples in here that summed up to 0. Then we run the same program, but now with a different input file. So in this case, it's a file that contains 2,000 integers, and the program comes back with the elapsed time as 2.643 seconds, and it says that there were 528 triples in that file that summed up to 0. Okay, so that's our implementation of a program that solves the threesome problem. Okay, now the question is, how do we figure out the time complexity of this problem, of this program? And in particular, we are interested in the time complexity of this method count, because that's the method that essentially solves the threesome problem. Okay, so what is the time complexity of this algorithm? So that's what we're going to discuss next. Now it turns out that you can figure out the time complexity of an algorithm in two different ways. The first approach is going to be is an experimental approach, and the second one is more of a mathematical approach. So let's start with the experimental approach. So what we can do is we can carry out an experimental analysis for the order of growth or the running time of a program simply using a stopwatch. All right. And we typically write the order of growth of a program or an algorithm as T of n, which is a function of n, where n is the input size. Right? So we write the order of growth or the running time of a program or an algorithm as a function T of n, where n is the input size. Right? So what we can do is we can figure out the running time of an algorithm using an experimental approach, where we simply use a stopwatch to get some data for the experimental analysis. All right, and we'll discuss that in a bit. So we're going to use this data type called stopwatch that we saw in our threesome program, and this data type is going to model a stopwatch. Okay, and its API is extremely straightforward. It supports a constructor that lets you build an object of type stopwatch, and then it lets you ask for the elapsed time in seconds since the stopwatch object was created. Okay, so this is the instance method that you will use to get the elapsed time. And again, these are the things that we saw in the threesome program. All right, so let's first discuss the implementation of the stopwatch data type. It's extremely straightforward. So it's called stopwatch. It has a single instance variable called start of type primitive long, and it is final, which means that start can take on a value only in the constructor, and then that value can never change. Okay, so that makes stopwatch an immutable data type. All right, so what are we doing in the constructor? Well, in the constructor, what we do is we get the current time in milliseconds by making a call to the static method inside of system. So that returns the current time in milliseconds, which we simply assign to the instance variable start. Okay, so that's the constructor. And then in elapsed time, what we do is we ask for the time now using the same method, current time in millis, which is a static method inside of system. And what we do is from that, we subtract the start time. All right. The start time is the time of creation of the stopwatch object. So we subtract that and we divide the whole thing by 1000 and return that value. So elapsed time correctly returns in seconds the elapsed time since the creation of the stopwatch. Okay, so that's the stopwatch data type. Now what we're going to do next is look at a client program of the stopwatch data type called doubling test that can be used to generate some experimental data for the Threesome program. All right, and that data will later be used to get a handle on the running time of the Threesome program. All right, so this program is called doubling test, and it's simply a stopwatch client. So let's see how it generates data for the Threesome program. Okay, so doubling test has two methods. It has a main method, and it also has this method called time trial. All right, so let's first focus on the main method. So what does the main method do? Well, it has this for loop where n starts at 250, and it is an infinite loop, so the Boolean expression is always true. So it's an infinite loop, and n is incremented as such, which is the same thing as saying n equals 2 times the current value of n. So in each iteration, the value of n is doubled, right? So n starts at 250, the next time around n is going to be a 500, next time around it's going to be 1000, and so on and so on and so on. And what do we do in each iteration? Well, what we do is we simply call time trial, which is the method above, giving it n as an argument. Okay, so now n is the input size. All right, so we call time trial in the first iteration with argument 250, then with argument 500, and so on and so on and so on. And what does time trial do? Well, time trial runs a Threesome the Threesome problem with size n. Right? And it simply returns the time that it takes to solve the Threesome problem of size n. And that value is assigned to time, which we then print as output. So for output, we print not only the time that it takes, but also the input size. All right. So the output is going to be a table where the first column is n, which is the input, size, and the second column is the time, meaning how long does it take in seconds to solve a Threesome problem of this size. Okay, so that's the output. It's a table. Now let's look at the time trial method. Well, the time trial method takes an input size, which is n, and then what it does is it sets a constant called max to the value of million, and then it simply creates an array A of primitive ints whose values are random numbers from the interval minus max to max, which is minus million to a million. Okay, and that's basically the input data for the Threesome program, right? So we first declare an array and create it with size capital N, and it's an array of primitive ints, and then we initialize each element in the array to be a random integer between minus million and a million. Okay, and we get a random integer using the static method uniform from the standard random library. Okay, so we have our input data for the Threesome program. So all that we need to do now is create a stopwatch object called timer, and then call the count method from the Threesome program that we discussed before, giving it the array A as an argument. All right, and then we simply ask for the elapsed time on the timer on the stopwatch and return the elapsed time. Right? Notice that here we are not interested in the count per se, meaning the number of triples that sum to 0. What we care about here is the time that it takes to solve the three-sum problem of a certain size. Okay, and that's what is being returned here. Okay, so that's how the program works. So let's look at some output. So when you run doubling test, you'll see that it just goes on forever, all right, generating this table as an output. And as I said before, the first column is n, the input size, and the second column is the time, which we can also write as t of n. And that's the time that it takes to solve a three-sum problem of size n. Okay, and that's reported in seconds. Okay, so that's now our experimental data. And from that, we want to get an estimate of the order of growth or the running time for the three-sum program. So let's see how that's done. So what we're going to do is simply plot that experimental data on in two different ways. We plot it here, where the x-axis is the problem size n, and the y-axis is the running time t of n. All right. This is the first column, this is the second column, and you have these points, and you fit a curve through it. All right. Now here on the right hand side, we take that same experimental data, but we plot it on a log scale. All right. So on the x-axis, what you have is not n but log of n, and on the y-axis, what you have is not tn but log of tn. Okay. Now, in the log plot, since the curve, it looks like a straight line, what we can do is we can use our good old formula y equals mx plus c to express this curve as simply the equation of a line, right? And that's what is done here. So we say the log of the y-axis equals some slope m times, so this is m, this is your y, m times x, which is log of n, that's the x-axis, plus some constant, which we write as log of a. Okay. Now the question is, how did we figure out that m has a value of 3? Well, that's very easy. You just go back to the experimental data and look at a couple of points. All right. Look at two values of x and the corresponding values of y, and simply use the formula which says slope is rise over run. All right. So if you go back to the experimental data from the previous slide, you'll see that for two values of x, log of 4k and log of 2k, the corresponding values of y are log of 6.4 and log of 0.8. So you can check this from the previous slide. All right. So we have that as rise over run, which can be simplified using log identities as log of 6.4 divided by 0.8, which is 8, and log of 4k minus log of 2k is simply log of 2k. So I'm just going to write it as log of 2. All right. Now, what is log of 8? Well, log of 8 can be written as log of 2 to the power 3, which is the same thing as log of 2. And that's divided by log of 2. So these guys cancel out, and what you have is 3. So that's how we got 3 for the slope, right? Now, the next thing that you can do is you can express this equation in this manner. All right, so these two are absolutely equivalent. Okay, and the way you get from here to here is by simply raising both sides to the power e, for example, or even 2. Right, assuming that these bases were 2. Okay, and then you can use some log identities again to arrive at this expression here. Alternatively, what you can do is you can take this expression and take the log of both sides and use some log identities to derive this guy here. Okay, so and you can do this as an exercise. So basically what I'm saying is these two guys are mean the same thing. All right. Okay, so now when you write it in this fashion, we have a nice expression for t of n. It is simply some constant a times the cube of n. All right. Now the question is, how do we figure out the value for a? Well, that's fairly straightforward. You simply go back to the experimental data and just grab like 1 point from that data. So for example, let's say n was 8,000, right? And from the experimental data, we have the corresponding value of the time taken as 51.1 seconds. So you simply plug that in into this formula, and you solve for a, and you get this for the value of a. Okay. So now we have everything. So we have a nice formula that expresses the running time or order of growth of the Threesome program in terms of the input size. All right, so it's some number, some constant times n cubed. Okay. So that's how we figure out the time complexity using experimental data. Now I should before proceeding, I should remark one point, which is that this number here depends on the computer on which you're running this program, on which the computer that you use to gather the experimental data. All right, so this is something that is machine specific. All right, whereas this part here of the formula, that is machine independent. Okay, and it is this part that we are more interested in for any algorithm. It's the part of the order of growth or running time that is machine independent. All right. So what that means is, no matter where you run the Threesome program, you will always get n cubed as this part of the expression for running time, whereas this constant here will differ. It's going to be different on different computers. Okay, whereas this term here, n cubed, is always going to remain the same regardless of which machine you use to run the Threesome program. Okay. Now it turns out that you can also address the time complexity issue using a mathematical analysis. All right, so you can derive a mathematical expression for the order of growth of a program. Now, to do that, you have to note that the order of growth of a program is determined basically by two things. All right, so it involves the cost of executing each statement. Okay, meaning how long does it take for a particular statement to execute, and that it turns out is a property of the computer on which you're running the program. Okay, and the order of growth also depends on the frequency of execution of each statement, meaning how many times does that statement execute in solving a certain problem. And that, it turns out, is the property of the program and the input, and does not depend on the machine on which you're running the program. Okay, so this is a very important idea. So let me repeat this. So what we're saying here is that the order of growth of a program is determined by the time that it takes to execute each statement, which is system or computer dependent, and the frequency of execution of each statement, meaning how many times does a statement execute, which is a property that is independent of the computer, and it only depends on the program and the input. Okay. All right. Now there's some notation and concepts that we need to pay attention to. So we're going to write f of n as an approximation of a function g of n. So this approximation is called the tilde approximation. And we do this to represent any function g of n that, when divided by f of n, approaches 1 as n approaches infinity. So what we are saying is we're going to use f of n as an approximation for g of n. All right. And let me give you an example of this. So let's say g of n is the function 3n cubed, or let's say 2n squared plus n plus 42, right? So g of n is this function, and what we can do is we can approximate the function g of n using the function f of n equals n squared. All right. And we can do this because the limit as n goes to infinity of g of n over f of n is 1. All right. So for large values of n, what we are saying is n squared is a very good approximation of the function g of n. All right. So in other words, the lower order terms simply don't matter when n is large. So that's what we are saying here. All right. So n squared, which is what we're going to use for f of n, is a pretty good approximation of g of n. All right. So that's one definition, that of tilde approximation. And then we are going to work with tilde approximations of the form g of n approximated by a times f of n, where f of n is going to typically have this form: n to some power b times log of n to some power c. Okay, and all these guys a, b, and c are constants. All right, and when that's the case, we're going to refer to f of n as the order of growth or running time of g of n. All right, so going back to the example that I gave you, so if g of n is 2n squared plus n plus 42, we will simply say its order of growth f of n is n squared. Okay, because we are in this case writing g of n as 2 times f of n, where f of n is simply n squared. All right, so we're going to say that n squared is the order of growth in this case. Okay. So what is the bottom line? The bottom line is that if you have a function like this, all right, then you can simply say, I mean, if the time that it takes for some algorithm to solve a problem of size n, if it is given by a function of this sort, then we can say that the running time of that algorithm is simply n squared. And that's a very good approximation for this function, provided n is large. All right, it's only the leading term that matters. The lower order terms don't matter, and even the coefficient of the leading term doesn't matter. Okay, so what really matters is the leading term with the coefficient disregarded. All right. Okay. So now let's carry out a mathematical analysis of the threesome program. Okay, so here what I'm showing you is the count method, the static method count from the threesome program that we discussed. So we saw this code before, and I have marked some certain regions of the code here on the right. All right, so this so A simply denotes this statement here. and then B denotes the outermost loop, so that's B, and then C denotes the second loop here, D denotes the third loop, and then E denotes this the statement here sitting inside of the if statement. All right, and what we want to do now is carry out a mathematical analysis of the order of growth or running time of this count method, which is the method that implements the threesome problem, all right, which solves the threesome problem. Okay, so let's go through this carefully. So in this table, what we are looking at is each statement block along with the time that it takes to execute that block, which is machine dependent. Okay, so going back to what we discussed before, so the time that it takes for a particular statement to execute depends on the system on which you run it. And then the next column is the frequency of that statement, meaning how many times is that statement executed. Well, that is a property of the program. It's not system dependent, all right? And then here we have the total time, which is simply the second column times the third column, all right? Okay. A is simply this statement here. Let's say the time that it takes for that statement to run is given by t sub 4, okay? And it's clearly executed just once, right? So the frequency is 1, so the total time is t sub 4. What about B? Well, B is this outermost loop, okay? And that's executed precisely n times, right? So the frequency is n. And let's say that the time that it takes for that loop to complete is t sub 3. So what is the total time? It's t sub 3 times n. And I hope it's clear as to why the frequency is n. Well, how many iterations do we perform in this for loop? It's precisely n, where I goes from 0 all the way up to n, not inclusive, okay? What about C? Well, C is the second loop. How many times is that going to be executed? Well, that's given by this expression n square over 2 minus n over 2, right? And let's say that time that it takes to execute that the second for loop is t sub 2. So the total time is just the product of the two, okay? Now, why is the frequency n square over 2 divided by n square over 2 minus n over 2? Well, this is basically the number of ways in which you select 2 items from n items, okay, where the order is irrelevant, okay? And this notation stands for n choose 2. Now recall that n choose 2 has a nice formula. It is factorial of n divided by factorial of 2 times factorial of n minus 2. Okay, but then what is this? This is simply n times n minus 1 divided by 2, and that's exactly what we have here, right? Because this can also be written as n square over 2 minus n over 2. Okay, so what this second for loop is doing is it's essentially looking at pairs of items, right? Distinct pairs from n items, all right? So that's what we are doing here. Okay, now what about D? Well, that's the innermost loop, okay? Now how many times is that executed? Well, it's the same idea. It is n choose 3 now, because what does this loop, the innermost loop, do? Well, it enumerates the triples from the collection of n items. So it's basically calculating n choose 3. In how many ways can you pick 3 items from n items disregarding order? Well, it is n choose 3, and this again has a nice formula, factorial n divided by 3 factorial times n minus 3 factorial, all right? And this simplifies to n times n minus 1 times n minus 2 divided by 6, because 3 factorial is 6, and this expression that you see here is essentially that, Okay, and you can actually simplify this and make sure that it is indeed what is shown here. All right. So that's the frequency of execution of the innermost loop. And let's say the time that it takes to execute that loop is t sub 1. So what is the total time? Well, it's just the product of these two guys, and that's what is shown here. Okay, and then E, which is this statement here, let's say that the time that it takes to execute that is t sub 0. Okay. What about the frequency? Meaning, how many times is this statement executed? Well, that's input dependent, and I hope you guys see that, because this increment happens only if this condition is true. Okay, and that clearly depends on the input numbers a at I, a at j, and a at k. Okay. All right. So we simply write the frequency as x. We don't know what it is. That depends on the input. All right. So the total time is t0 or t sub 0 times x. So what is the grand total then? The grand total is simply the sum of all these guys, which is what is shown here. So this is sort of like your function g of n, which is a crazy function. All right. But now we're going to use our tilde approximation idea and drop all the lower order terms. So drop that, drop that, drop that, and drop that, and what we get is that as the tilde approximation of g of n. Okay, it's just the leading term that matters, assuming that x is fairly small. And then the order of growth is simply this expression with the coefficient ignored. Okay, so the order of growth is simply n cubed. So it turns out that when n is large, it's really this term that matters. Okay, and the other terms, the lower order terms, and this coefficient here does not matter at all. So the running time. So what are we saying? We are saying that the running time for the threesome problem through this mathematical analysis is simply n cubed, or in other words, the threesome program, the way that we have implemented it, is a cubic algorithm. Okay, that's basically the bottom line. And notice that this was obtained using a mathematical analysis, and then in a previous slide we obtained the same order of growth or running time, okay, using an experimental analysis, and they very nicely agree. All right, so both the experimental analysis and the mathematical analysis tell us that our solution to the threesome problem, which is basically this count method, is a cubic algorithm. All right, so the running time varies as the cube of the input size. Okay, now for many programs, developing a mathematical model of the order of growth boils down to the steps that are shown here. All right, you need to develop an input model which includes the definition of the problem size, and then you need to identify the innermost loop in your program, and then you need to define a cost model that includes the operations in the innermost loop, and finally you need to determine the frequency of execution of those operations for the given input. Okay, so these are the steps that you need to perform in doing a mathematical analysis of the order of growth of a program. All right, so for the threesome program, what do these things correspond to? Well, the input model is simply a collection of n numbers, right? That was your input, and the input size is simply capital N. And what is the inner loop? Well, the inner loop is simply the if statement that sits inside of a triply nested for loop. So you just have to go back to the code, and you'll see that the inner loop is simply the if statement that is buried inside of the innermost loop. Okay, and what is the cost model here? Well, the cost model for the threesome program is simply the number of times you access the array A, all right, in that inner loop. Okay, so that's the cost model. And finally, what's the frequency or the number of times you access that array in the inner loop? Well, it is n cubed over 2. Why is it n cubed over 2? Well, if you go back to the previous slide, the that if statement, that inner loop is accessed n cubed over 6 times, right? But in that if statement, how many references do you make to that array? You make 3 of them. It's a at I, a at j, and a at k. Okay, so it's basically 3 times that, which is n cubed over 2. Right? So that's how you get this number. The frequency of array accesses is n cubed over 2. Okay? So that's what you need to do if you were to carry out a mathematical analysis of the running time of a program. You have to follow these steps, right? And that's exactly what we did for the Threesome program. Okay, so now here in this table, I'm showing you the popular order of growth classifications, all right? And the first column here gives you the name of the classification. The second column tells you how you write it in mathematics. And then the third column gives you the code description for that particular class, meaning how does it manifest itself in code, right? And then the last column gives you an example. So for each class, you have some example in mind of a program that belongs to that class. All right, so let's go through this table carefully. So the very first class is the constant class, and that in math you simply write as 1. So what this means is here the program simply, the running time does not depend on the input size. So regardless of what the input size is, the program runs in constant time. And this is like the best possible order of growth, okay, where your algorithm simply, the running time of the algorithm simply doesn't depend on the input size, okay. So a good example to keep in mind is just adding 2 numbers, right? So that has a constant time performance. Another example to keep in mind is array access, okay. So let's say, you have an array A, and you're trying to access the ith element from it. Well, this operation of indexing an array is a constant time operation. It doesn't really depend on how big A is, right? So this is extremely fast. Okay, and what is the code description? Well, it's just a single statement. So for example, if you have something like A at I plus plus in code, then this statement is a constant time operation. Okay, it doesn't depend on the size of A. Okay, and then the next class is the logarithmic class, where you write the running time as log of n, that's notation. And then what is the code description? Well, when in a program you divide your input into 2 halves, and if you disregard half of the input in each step, then that code has a running time that is logarithmic, right? And a good example to keep in mind is binary search that we're going to discuss in a bit, right? The next class is the linear class, that is written as such. So you simply write t of n equals n, and then the way that manifests itself in code is as a loop. Okay, so if you have a loop that that looks like for I equals 0, I less than n, I plus plus, and so on. So this loop is clearly linear, okay, meaning it's iterated n times, right? And a good example to keep in mind is finding the maximum of a collection of n items. So if I give you an array A that has n items, how do you find the maximum value in that array? Well, you do it using a single for loop, okay? And that code will have a running time that is linear. The next class is the linearithmic class, which we write as n log n, and this typically manifests as a divide and conquer algorithm in code, all right? And a good example to keep in mind is merge sort, which we will discuss in a future lecture when we talk about sorting algorithms. The next class is quadratic, that we write as n squared, and this typically manifests itself as two nested loops, double loop. And a good example to keep in mind is enumerating all pairs. So if I give you n numbers and I ask you to print out all distinct pairs, then you would set it up as a double loop, and that has a running time that is quadratic. The next class is cubic, which we write as n cubed, and this shows up as a triple loop, like the threesome problem, for example. And a good example here to keep in mind is checking all triples, right? Enumerating all triples. And then there is the exponential class that you write as 2 to the power n, and this typically involves exhaustive search, meaning searching through an entire space. And a good example to keep in mind here is checking all subsets. So for example, if I give you three sets, a set containing 3 elements, A, B, and C, and if I ask you to print out all the subsets of this set, well, how many subsets do you have? Well, you have the empty set, and then you have the sets that contain exactly one element. So that's that. Sets that contain exactly 2 elements, so AB, BC, and then AC, and then the set that contains everything, ABC. Okay, so the number of subsets that you have for this set with 3 elements is basically 8. So you have 1 plus 3 4 plus 3 7 plus 1 8. Right? So in general, if you have a set with n elements, there are 2 to the n subsets. So if I ask you to print all the subsets of a set with n elements, you have no choice but to do an exhaustive search over 2 to the n subsets of that set. Okay, and that's an example of an exponential algorithm. Okay, so these are some of the popular classes. Now keep in mind that this is not, this exhaustive by any means. Okay, there are other classes that sit sort of between these guys. But the ones that are considered in like good running times are everything from constant all the way up to linearithmic. All right. Anything beyond that really don't scale very well with input. Okay, so you should try very hard to get your algorithm to belong to one of these classes. All right, if possible. Of course, at times that's just not possible. For example, when you're, if your input, if your problem is to print all the subsets of a set, you have no choice but to go do an exhaustive search. All right. To give you another concrete example, if I ask you to add 2 matrices that are n by n, you have no choice but to implement an algorithm that is quadratic. You cannot do any better than that. Okay. But at times, through clever tricks, you can improve on the implementation of an algorithm and take it from one particular class and put it into a better class. Right? And we will see an example of this very soon. Okay, so these are some of the popular order of growth classifications. And here we're simply looking at the plots of these different classifications. All right. On the left hand side, it's on a regular scale, linear scale, and on the right hand side, it's on a log scale. All right. And the best algorithm is the constant time algorithm that you see in blue, and the worst is this guy here in black, which is exponential. All right. And then the others are shown in different colors, and the same thing here, but on a log plot. Okay, so now let's talk about some algorithms and discuss their running times. So we're first going to talk about the search problem, where you're given a collection of n keys or n items, and you're asked to look for a particular key in that collection. Okay, and if you manage to find that key, then you simply return its index in the collection. And if you don't find that key, you're supposed to return -1 or something like that. All right. So that's the search problem. You're given a collection of n keys and you're asked to look up or search a particular key in the collection. So one way to do this is using what is called a linear search, and here is a Java method that does that. It's a static method called indexOf that takes a collection A as the first argument and takes the key that you want to look up as the second argument, and then it simply does a linear search. So I goes from 0 all the way up to the length of the array in increments of 1, and then you check if the element at I is the given key. And if there is a match, you simply return I, saying that the key was found and that it was at that index in the array. But if there is no match, you keep going and you look at the next element in the array and compare it with the key and so on. And then if you don't find the key in the collection, you end up returning -1, saying that the key was not found. So the question is, what is the running time or order of growth of this algorithm? Well, it's very clear that in the worst case, you have to look at all the elements in this array in order to search for this item. Okay, and how many items do you have here? Well, you have n of them. So in the worst case, this is a linear algorithm. All right. What about the best case scenario? Well, the best case scenario is where this key that you're looking for is the very first item in the array. In that case, you simply, you find the key in the very first iteration and you return its index. So that's the best case scenario. And in the average case, you have to do about n/2 comparisons. Okay. So for this algorithm, the best case running time is constant. The average case running time is n/2 comparisons, and the worst case is n, which is what is shown here. Okay, so that's how linear search works. Now let's look at a more sophisticated search algorithm, which is called binary search. Right? Now for binary search, again, the input and output semantics are the same. You're given a collection of n keys and you're asked to look up a particular key, and you're supposed to return the index of the key if the key is in the collection, or -1 if it is not. Okay, so the input and output are the same, but for binary search to work, the collection has to be sorted. So if the collection is not sorted, then you simply cannot carry out a binary search. So let's take a concrete example. So this is my collection A, and notice that it is completely sorted. Okay, lowest element here and the highest element there. And let's say we want to look up a certain key 23 in that collection. So how does binary search work? Well, we maintain 3 pointers: low, high, and mid. Low points to the first element, high points to the last element, and mid points to the middle element. Okay. And then what we do is we compare the given key 23 with the element that is pointed to by mid. And if the given key is smaller, then we know that since the array is sorted, that we're not going to find the key in the right half. Okay, so what we do is we repeat binary search on the left half. All right, and then we continue the process. So let's see how things work for this particular lookup. So we are looking for 23. We compare it with 33. Well, 23 is smaller than 33, so there's no way we're going to find it here. So what we do is we adjust the high pointer now and make it to point to this guy here, which is what you see here. Low continues to point to 10, and now the new mid is the middle point of a low and high, which is this element here, 16. And then we repeat the process. 23 is compared with 16. 23 is larger than 16, so there's no way you're going to find 23 here because the input is sorted. So what do you do now? Well, you adjust low to be that element, which is what you see here, and then high remains where it was, and the new mid is pointing to this guy here. The same step. Repeat the process, compare 23 with the element pointed to by mid. Well, now you have a match, so you're done. You simply return the index of this element 23, and you're done with binary search. Okay, so you managed to look this up in using just 3 comparisons. Okay, let's take another example where we do an unsuccessful search for a key. So let's say we are looking for the key 50 in the same collection A. Right? So how does the algorithm work? We start with low at the first element, and then high at the last element, and mid pointing to the middle guy. And then we compare 50 with 33, because that's what is pointed to by mid. Well, 50 is larger, so there's no way I'm going to find 50 here. So you repeat binary search on the right half. So you adjust low to point to this fellow, high continues to point at 98. You have a new mid, so you compare 50 and 68. 50 is smaller, so you disregard this part of the input. And now high points to this guy here, 57, low pointing to 48. You have a new mid. Now you compare 50 with 54. It's smaller, so you need to go to the left. So now you have a scenario where all these guys point at 48. Now you compare 50 with 48. Well, it's larger, so low is now adjusted to point to this element, and high continues to point at 48. But now notice you have a scenario where low and high are on the opposite sides, right? And this is where you terminate the algorithm. So this is where you terminate, saying that the given key was not found in the collection, and you return -1. Return -1. Okay. So you stop whenever when the low and high pointers cross sides. That's the termination condition. Okay, for the binary search algorithm. All right, so that's how binary search works in principle. So let's see how it's implemented in code. So this program is called binary search, and it has two methods: a static method called index of that does the binary search. It's given an array A, a collection A of n items, and a key to look up, and it's supposed to return the index of this key in A if the key is found, and -1 otherwise. Okay, so let's see how it implements binary search. So we start low, the low pointer at the first element, and we start the high pointer at the last element. So that's a dot length -1. Okay, so 0 for low, a dot length -1 for high. And then as long as low is less than or equal to high, we continue doing binary search. Okay, so and this loop terminates precisely when low is strictly greater than high, meaning low and high have swapped sides, in which case you end up returning -1, meaning that the key was not found in the collection. Okay, but if this condition is true, then what you do is you calculate the middle pointer as low plus high minus low divided by 2, and then you simply compare the given key with the element in A that is pointed to by mid. Okay, and if the given key is smaller, then you know that you cannot find this key on the right half. Okay, so in that case you adjust the high pointer and make it to be mid -1. So now you continue doing a binary search on the left half. So that's what this means. But what if the key was strictly greater than the middle element? In that case, you know that you're not going to find the key in the lower half, so you adjust the low pointer to be mid +1, meaning you do binary search on the right half now. Okay. Otherwise, you have a match, meaning key matches A at mid. In that case, you simply return mid, the index of the key in the collection A. So this is what you do when you have a match. Okay, so that's binary search. Now let's talk about the main method. So here you receive a command line argument, which is a name of a file. All right, and this file is what we call a whitelist file. Okay, and we read it using the in data type. We make a single call to read all ints, and we get the contents of that file, which in this case is just, an array of integers, which we call whitelist, right? And then what we do is we make a call to the static method sort from arrays to sort that collection whitelist. Why are we sorting? Well, because we would like to perform binary search on this collection, but recall that for binary search to work, the collection has to be sorted. Okay, so we need to first sort. And then what we do is in this while loop, we receive input from standard in. These are integer inputs. So as long as standard in is not empty, we get some key, as an integer from standard input, and we look it up in the whitelist collection, right, using binary search, which is this method. So we simply call this method, we say binary search.index of, and we give it whitelist as the first argument, the collection, and the key that we got from standard in as the key that we want to look up. And if index of comes back with -1, what does it mean? It means that this key is not in the whitelist. So what do we do in that case? We print the key. Okay, so what we are doing here is we are basically printing the keys from standard in that do not exist in the whitelist. All right, that's what the program does. Okay, very good. So let's look at some input and output. So here is a whitelist file that contains all these numbers. And here is another file that we're going to feed in to the program via standard input, right? So how does the program behave? So we run binary search, giving it the whitelist file as a command line argument, and we feed in this file that we call the transaction file as standard in, right, using the redirection operator. And what does the program print for output? Well, it's printing numbers from here which are not here. Okay, so what the program does is for each number here, it looks it up in this collection using binary search. Okay, binary search, right? So it looks up 23, it finds it. It looks up 50, it doesn't find it, so it prints it. It looks up 10, it finds it. It looks up 99 using binary search, it doesn't find it, so it prints it, and so on and so on and so on. So what you see here for output are the numbers that are in the transaction file that are not in the whitelist file. Okay, all right, so that's how the program works. Now, what is the order of growth or running time of binary search? Well, it is log of n. So this is an example of a program where we are constantly dividing the input into two halves, and we are throwing away one of the halves, right? And whenever you do something like that, the running time of your program is logarithmic, all right? So that is indeed the running time for binary search. And as a result, binary search is extremely efficient, okay? Because the log function grows extremely slowly. All right. So to give you a concrete example, if n is, let's say, million, right? What is log n? So log n is approximately 6. So what we are saying here is, even if your collection has about 1 million elements, it would take only 6 comparisons to look up a certain key, right? So that's extremely efficient. Okay, but just keep in mind that for binary search to work, your collection has to be sorted. Okay, now what is the order of growth of the program itself, of the binary search as a program? Meaning, what's the running time of the test client? Well, binary search itself, a single binary search in a collection of n items is log n. But let's say you're doing m such searches. So what is the running time then? Well, it is m log n. All right, and that's exactly what binary search did. It did m searches in a collection of size n, right? So the running time of binary search program, meaning the client program, is m log n, where m is the number of calls to binary search.index of, or in other words, it's the number of binary searches that we perform. Okay. Now, before we proceed further, let me mention one thing, which is that how do we compare, a linear search and binary search? I mean, how do the two algorithms compare with each other, and when is one better than the other? Well, linear search and binary search. Linear search has a running time of n, and binary search has a running time of log of n, okay, on a collection of size n. But keep in mind that for binary search to work, the collection has to be sorted, all right? And sorting is not doesn't come for free. So that in itself has its own order of growth or running time. So even if you use the best sorting algorithm in town, the running time is n log n. All right, it's a linearithmic algorithm. So the total running time for binary search then is that much for search and that much for sort. All right. So if you're just doing one lookup in a collection of n items, linear search is much better than binary search, right? And it's clear from these expressions, right? So you don't really benefit from binary search if you're just doing one lookup or even a few lookups. The place where binary search really excels is when you perform m searches, right? And where m is much bigger than n, right? So in that case, so if you're performing m searches, then and if you do linear search, in that case the cost of linear search is going to be m times n, m searches, where each one has a cost of n, and on this side it's going to be what? So this is interesting. If you're performing m searches, then you incur the cost of sort just once, all right? Because the collection doesn't change. So you just sort once, and then you perform m binary searches. So this is m log n, all right? And this is significantly less than m times n, if m is much bigger than 1, meaning many searches, right? So you gain from binary search only when you're performing many binary searches on a collection that is static, right? Meaning you just have to sort once, right? Okay. And now the next thing that we want to talk about is how do we improve on the algorithm that we discussed for solving the threesome problem. So we came up with an implementation for the threesome program that involved 3 nested for loops, and we also analyzed it both experimentally and mathematically and figured out that the running time in that with that implementation was cubic, right? So now the question is, can we do better than that? Can we improve the order of growth classification of threesome from cubic to something better? And the answer is yes. So it's a very clever trick that you perform to improve the performance of threesome. And here is how it works. So this version of threesome is going to be called threesome fast. And it also has 2 methods, just like threesome. It has a count method that takes an array of n integers and returns the number of triples that sum up to 0. And then it also has the main method that is identical to what we saw before. It gets a file as a command line argument that contains n integers. It reads the file into an array of ints called a, and it simply calls count with that array as an argument and prints the number of triples that add up to 0. Okay. So now let's look at the count method to see in some detail to see how this is an improvement over the previous one. All right. Okay, so the first thing that we do is we get the size of the array as capital N, and then we sort the given array. Okay, we sort it because we're going to be using binary search to solve the threesome problem. Okay, and binary search expects the collection to be sorted. So we do that. Now here, let me just make a note that even if you use the best sorting algorithm, this running time is n log n. I mean, assuming you use the best algorithm, which is what we are doing here, the running time is n log n. So I've just made a note of that. And then we initialize a variable called count to 0. That's going to keep track of the number of triples that sum to 0. And then what we do is we have 2 nested loops, not 3, all right, like the previous implementation. So the first loop goes I equals 0 all the way up to I less than n, increments of 1. And then j goes from I plus 1 all the way up to n in increments of 1. And then what we do is something extremely interesting. So we are looking at items a at I and a at j. All right, and then what we do here is we say if we do a binary search on the collection A for the item that is the negative of a at I plus a at j. Right? So what we are saying is that if we manage to find the negative of this number in the collection A, then we have managed to find a triple that sums to 0, right? Because we are looking at items a at I and a at j, we have found the negative of their sum in the collection. So what that means is this number plus a at I plus a at j plus the minus of that is 0, right? So in that case, we simply increment count by 1. All right, and notice that we are looking for the negative of a at I plus a at j in the collection, and we are insisting that its index be greater than j, right? And this is just to make sure that this is a number that we have not seen before. Okay. And this goes back to what we said earlier about finding distinct triples A, B, and C such that A plus B plus C equals 0, right? So what to summarize, what we are doing here is basically we have items A at I and A at j, and if we find the negative of their sum in the collection A, then we know that we have a triple that sum to 0. Okay, in which case we increment count by 1. All right. So now, how is this an improvement over the previous implementation? Well, it's an improvement for the following reason. So let me make a note here that the running time of sort is n log n, assuming you use the best sorting algorithm. And how many times is this if condition executed? Well, it is sitting inside of like a double loop. So this guy is executed precisely n square times. Okay, and then what are we doing in each such iteration? Well, we are doing a binary search. And what is the running time of binary search? It is logarithmic. So the cost of this if statement is basically n square log n. Okay, so the if statement is executed n square times, and in each time you're doing a binary search whose cost is log n. Right, so the total cost of the if statement is n square times log n. So what is the running time of count now? Well, it is n square log n plus n log n for the sort. That's this part here, right? So these are the two like significant costs in this method count, right? And now, so this is like our g of n. Right? Now we use the whole tilde approximation idea. So we completely ignore the lower order term, and we say that g of n is approximated by f of n, which is n square log n. All right, and you should try and convince yourself that n square log n is significantly smaller than n cubed, which was the cost of our previous implementation. All right, for large values of n. Okay, so this new implementation is indeed an improvement over the previous implementation. All right, and we've managed to improve the performance of this algorithm using a very clever trick, namely binary search. All right. And it's not at all obvious. It wasn't obvious in the first place how you could have used binary search to solve this problem. And this goes back to what I said before. Sometimes it's not obvious on how you improve the order of growth class of a particular algorithm, but through clever tricks you are able to do so, and that's what we have shown here, in this program, Threesome Fast. Okay. So the order of growth for this implementation of a solution for the threesome problem is n squared log n, right? Which is much better than n cubed. Okay, so we are done with our discussion of the time complexity issue of an algorithm. What we need to discuss next is the space complexity aspect, meaning how much memory does a program take in solving a certain problem. Okay. But to talk about that, we first need to discuss what are the memory requirements for primitive types. Okay. So it turns out that a Boolean in Java takes up a single byte. A byte takes up a byte, char 2 bytes, int 4 bytes, float 4 bytes, long and double each 8 bytes. All right. So if you, for example, if inside of your a method in your program you make use of 3 ints and a double. All right. So let's say for the sake of argument that you have 3 integers and 1 double. So what then is the memory footprint of that method? Well, since you have 3 integers, it is 3 times 4 because each integer is 4 bytes, and then since you have a double, it is 1 times 8 because a double is 8 bytes. So how many bytes is this? This is 12 plus 8, and that's 20 bytes. Okay, so that's how you basically get an estimate of the memory footprint of a method that uses primitive types. Okay, now to determine the memory usage of an object, what you do is, it's fairly easy. You simply add the memory requirement for each instance variable along with the overhead associated with the object, which is typically 16 bytes. So there is a 16-byte overhead for each object, and in addition you have the memory, the amount of memory for each of the instance variables in that object. Okay, so let's take a concrete example. So let's look at the counter object. Okay, so the counter object has a memory footprint of 32 bytes. Well, how did we figure that out? It is 16 bytes of overhead, which is that guy there. And then if you remember, the counter data type has 2 instance variables. It has a string instance variable for the ID, which is 8 bytes, it turns out. And then it also has an integer instance variable to keep track of the tally. An integer from this table is 4 bytes. Okay, so what do we have? We have 16 plus 8, which is 24, plus 4, which is 28, and then there is also 4 bytes of padding. All right, and this is basically for memory alignment reasons. And that gives us a total of 32 bytes. So if you have, two counter objects floating around in your program, then what is its memory footprint? It is 2 times 32 because each counter object is 32 bytes, and that is 64 bytes. Okay. To go back to an example that we discussed earlier, where we used, and this program was called flips or something like that, where we created 2 counter objects to tally the number of heads and tails out of capital T number of coin flips. There, the memory footprint was something like 64 bytes because we had 2 counter objects, heads and tails, right? And each counter object is 32 bytes. Okay, so that's how you estimate the memory footprint of an object. Now, what if you have a non-static inner class inside of another class? Right? In that case, you need an extra 8 bytes of overhead because the inner class needs to maintain a reference or a pointer to the enclosing class. right? So that's what we're saying here. A nested non-static inner class requires 8 bytes of overhead, which is in the form of a reference to the enclosing or the parent class. What about an array? An array of primitive type values requires 24 bytes of header information, all right? And that includes 16 bytes of object overhead plus 4 bytes to keep track of the length of the array and 4 bytes of padding. So it's 16 plus 4 plus 4, which is 24. So if you have an array of primitive values, there is 24 bytes of header information, right? And in addition, you have the memory that is needed to store the values in the array. Okay, so let's take a concrete example. So let's say you have an array of n primitive integers. Okay, so what is the memory footprint of such an array? So let's say you have an array A that stores n primitive integers. Well, there is the 24 bytes of header information, and then since the array has n primitive ins, that has a memory footprint of 4 times n because each integer is 4 bytes in Java. Okay, so the total memory footprint of an array of n primitive ins is 24 plus 4 n bytes. What about an array of objects? So an array of objects is an array of references to objects. Okay, so we need to add the space for the references to the space required for the objects themselves. Okay? Let's look at an example. So let's say you have an array of n date objects, right? Well, since it's an array, you have the array overhead, okay, which is 24 bytes, and then you also have 8 n bytes needed for the references, right? Because what you have is an array 0, 1, and so on, all the way up to n minus 1, and each element here is a pointer to a date object. Okay, and it takes 8 bytes for each pointer, for each reference. There are n items, so you have 8n bytes for the references. And in addition, you have 32 bytes for each date object. Right, so each date object is 32 bytes. So what is the total? Well, 24 bytes of header information plus 8n plus 32n, which is 24 plus 40n bytes, right? So an array of n date objects occupies about 24 plus 40n bytes in memory. What about a two-dimensional array? Well, in Java, remember that a two-dimensional array is simply an array, a one-dimensional array of one-dimensional arrays. Okay? So you might have m rows and n columns. So what is the memory footprint of such an array? Well, let's take a concrete example where the two-dimensional array is an m by n array of doubles. So let me draw this picture again. So you have a one-dimensional array with m rows, each pointing to a one-dimensional array with n columns. So what is the memory footprint of such an array where each element is a primitive double? Well, since we have this one-dimensional array, there is the 24 bytes of overhead for that array. All right, and now this array has m elements, and each one is a pointer or a reference to a one-dimensional array, and each reference is 8 bytes. So you have 8 m references to the row arrays. Okay, these guys, and then you also have these individual arrays, each of which has an overhead of 24 bytes. Okay, but how many such row arrays do you have? Well, precisely m of them, each one with a 24 byte requirement for the header information, right? So that's 24m. And then finally, you also have 8mn as the requirement for the m times n primitive doubles that are sitting inside of the array. Okay, and each double is 8 bytes. So to store m times n doubles, we need 8 times m times n bytes. So the grand total then is 24 plus 8m plus 24m, which gives you 32m. So it's 24 plus 32m plus 8mn for the m times n doubles. Okay, and this if you use the tilde approximation, is simply 8mn, because when m and n are large, these lower order terms really don't matter. Okay, so you can simply say, so even with space complexity, you can use this notion of a tilde approximation and say that this expression on the left can be approximated using this expression on the right. Right? So that's how you estimate the memory footprint of a two-dimensional array. Finally, what about a string? Well, a string of length n, so if it's a string with n characters, it uses 32 bytes, okay, for the string object, plus 24 plus 2n bytes for the array that actually contains the strings, to give you a total of 56 plus 2n bytes. Right? Because internally, what a string does is it simply uses an array to store those characters. Okay? And since it's an array, it has an overhead of 24 bytes. And since it's an array of n characters and each character is Unicode or 2 bytes in Java, we have 2n bytes. Right? So it's 24 plus 2n bytes. And in addition, since string is an object, there is this requirement of 32 bytes. Right? So the grand total then is 32 plus 24 plus 2n, which is 56 plus 2n. And here again, if you're dealing with a giant string, you can approximate this using tilde approximation and say it is simply 2n bytes. Right? The 56 doesn't really matter when n is big. Okay, so that ends our lecture on analysis of algorithms. And with what we have discussed so far, I hope you have a good idea on how you go about figuring out both the time complexity and the space complexity of an algorithm. All right. So thanks for your time.